24th hertz right here, just one electron. So the mc squared is just huge. How can we throw something so huge away? Well, very easily, because all we're interested in our experiments is the differences in energy. We don't actually measure directly energy. We're interested in the beats between levels, not the actual values of those. We've made that point with our two-level things, right? That's what you see in the beats, the differences you see. So, and the differences, the mc squared cancels out. Then you can throw it away. That's your gauge, so to speak. Okay? But if you're really going to play with having light make matter and back matter coming out of light colliding, or matter colliding giving light, the pair production, pair annihilation is the most elementary process, then you got to bring this guy back and start using this guy. So the Schrodinger equation becomes a Klein-Gordon equation when you take this into account. Okay. And Niels Bohr then starts to use that, and that's where quantum mechanics really made its money, is through Bohr's models. Okay. Now the other thing that's here, and we're not mentioning that, and I'm very much remiss in not having figured much out about it, but this is all stuff with phasors that go clockwise. There's a whole nother hyperbola down here where they go anti-clockwise. That's the stuff that goes backwards in time, so to speak. So there is that to worry about. We're not going to do that very soon. I hope to do it soon, but it's one of those things that keeps going day, tomorrow. Right. Okay, so we've been remiss in keeping all of this stuff going on the table. Anyway, here is where you get to actually see, and that's kind of the punchline to this derivation. I mean, we basically derived the basic pieces of the quantum mechanical quantum matter, the very fundamental parts of it. Well, you eventually make the equations that you learn in quantum mechanics. So this table right here that has the Lorentz contraction, the Einstein dilation, we've been looking at in the last lecture, and then this one that's linear in the rapidity or the stellar aberration angle, the hyperbolic sign, that's the past-future asymmetry. So one of the things you notice by looking at this is that infinitely fast phase thing, it goes up linearly, while the motion from going to some higher speed from the bottom of this hyperbola, you see, I can go a long distance here. I mean, quarter the speed of light, you know, is kind of out here where I start to see, my gosh, I have something here that's quadratic. But this, from here, it's constant, you see. So the effects that we talk about in relativity, second order effects, they're not noticeable in most of the classical mechanics we do, where we keep everything under an electron volt or so in energy. But eventually, it too has to. This one's linear. These two right here are, for the most part, second order Doppler shifts. That's really what it's coming down to. But here, you see what's going to happen, and we can see this from the geometry pretty easily, especially when we start using the sigma angle. It turns out to be the polar angle of the Lagrangian, and it's sitting in this graph right here. The Hamiltonian, very obviously sitting there as a hyperbolic cosine. So this guy right here that has a hyperbolic cosine, if you plot that correctly and turn it over, you've got the St. Louis arch, right? We're talking about catenary, right? At least for a while, it's really a hyperbola, which is where the catenary comes from. So here's the Hamiltonian taking the place of time dilation. Here's the Lagrangian, as we're going to show, taking the place of the contraction, that miraculous thing that waves do, is second order Doppler squeezing. Well, this is the thing that's keeping track of that. Then the inverse of this guy is a de Broglie, and then there's the phase velocity versus the group velocity. So remember, on both of these tables, they're identical except for their physics. Everything on this side is inverse of the corresponding position here. This is inverse of that, and this inverse of that, and this inverse of that. So it's a highly inbred theory. It's got all of these things that get used over and over again, which can be very confusing. But here we try to separate that. Okay, now, what about matter? How many kinds of matter? It seems that we sort of be a little blasé about this particular constant here. Rest mass has got something in it really vibrating fast, and that thing right there has got even more vibration as you pick up your momentum. So question is, as I ask, what's the matter with mass? This elephant is in the room, as elephants prone to do when something's weird happening that no one wants to talk about. Okay, he says he wants you to talk about it. He says, I matter. And the question is, how much kinds of matter are there? You see, what we're trying to do is get rid of some words that we think we know what the meaning is. We think we have a feeling for energy, but if you ask somebody that's giving a lecture on energy, like I did Art Husband one time, I said, how do you define energy? And he says, oh, well, it's just a measure of how much work you do. And I says, well, how do you define work? And he says, well, that's energy, I guess. So you're around in a circle with, a word that you're supposed to be used to, but you realize, that's something we should need. Well, what we're saying here, that's inverse time, with something in there to make it the joule unit that you're used to. Okay, momentum, sort of inverse space, but we got to talk about this one. This one has a little bit more structure, and then of course we feel we're pretty confident about what velocity is, but it's going to turn out to be a derivative. In fact, you can see that on the graph that we've got here. And in that, if this is a plot of the energy dispersion, the tangent to that line right there, the slope of that thing is the group velocity. And the group velocity is sitting right in this territory here. So that distance here is the group velocity. We haven't written that in there, but there's a hyperbolic tangent from here to there that's written very clearly in the no, let's go with this, what I handed you today. Actually, come to think of it, I did not have that annotation. That's something you're going to put on there. But the basic idea then is, here's one kind of mass that very famous kind of mass. That is, if you take that enormous frequency, okay, that you have, say, for an electron, 10 to the 24th or so per second, and you put here an h bar on it. Now the h bar it is in our units just around 10 to the 30 minus 34 joule seconds. So that tames this down a little bit, but you've got this huge number in the denominator. Okay, so you've got a small number here, a pretty large number here maybe, depends on your mass, but then another large number in the denominator, so that makes the actual rest mass of this box of light, say it's in a cavity or it's in the waveguide moving along, you get a very tiny mass for a box of light, 600 terahertz, cranked up as much as you could crank a laser. You really are in the neighborhood of 10 to the minus 48 to 10 to the minus 45 kilograms. That's pretty small, not something you're going to put on a scale and weigh right off the bat. But we all knew from Einstein's theory that if you put energy into something, that it's got to have extra matter. This is showing you how that happens. Okay, you're in there and it's bouncing around, you start to accelerate, it's going to be a little bit, 10 to the minus 44% less easy to accelerate that cavity. But the mass that you're talking about is so small compared to the actual Ingvar steel that's holding that way, right? So we would never claim to be able to measure that any way we know now. That makes things very small, and the nano, and beyond, it starts to actually play with you. But there's a thing called momentum mass. That is definitely part of any relativity course. And so what I'm going to do here to get that is I'm going to say, all right, I've got a new formula for momentum here. It's not m v squared or p squared over 2m anymore. That's 200, but this one is mv or p. And I'm putting a c on it right there to get rid of this so this is linear, you see. That is the velocity, that's the group velocity. We're going to take the group velocity, which is the slope of that tangent to the hyperbolic course. We're going to use these new as of 1900s, 1921 formulas, and we're going to stick them in our definition of momentum, okay? That is, that momentum would be a velocity times a mass. Okay, so I'm looking here just at the mass. I'm going to divide the velocity into the p, but I'm going to use these new guys. All right. Well, hyperbolic sine. This is hyperbolic sine over cosine. When you get done doing that, you see very quickly that you're going to be getting this very famous formula for momentum mass, which is just the hyperbolic cosine. Okay. So this hyperbolic sine lives in this thing. Cancels this sign, but I have a 1 over cosine now. That comes up on the numerator, gives me that. Okay, is that clear? So that one's pretty easy to sort of psych out. That's just getting a feeling for what these quantities are. What you're seeing is that the idea of mass is very fungible. Okay, now the limiting cases, as you go towards C, is the rest mass, which does not change. That's the bottom of the hyperbola does not change as you accelerate past it. You've got this e to the rho as the main part of the hyperbolic cosine, so it goes up exponentially. And this is a lesson here. Most of what's going on in this business is exponential. Okay, all of the crazy things that are going on way out in space. Most everything is happening exponentially. And this is just the beginning of that. But as you approach C, the momentum mass becomes the rest mass. And we don't talk about different kinds of mass in classical physics. Here you start to do that. Okay? Well, how about Newton's idea of mass? This is Galileo's. What about Newton's idea of mass? Okay, the idea of the ratio of a force to an acceleration. Well, the whole idea of the acceleration being a rate of change of velocity. Okay, or basically what we're doing here is we're going to take the derivative of p over the derivative of u, and see how that relates. Okay, so typical dp here, if I use the p that I have there, I take the derivative of that, and I get a hyperbolic cosine from a hyperbolic sine, and then this guy right here is the derivative of the hyperbolic tangent, that's sec squared. Put those two together, okay, in a dp over du, you get this. Okay, well, that's kind of neat, because this is hyperbolic, inverse hyperbolic cosine, so it's two of those factors are going to come up here. You get this weird thing. Instead of the first power, it's the third power. That's called effective mass. Okay? Well, that's kind of neat. This one's going to go up as a triple product of the exponential. But for low speed, it's going to come back and be rest mass. Okay, so rest mass is what you'd expect you should get from all of these analyses. Now here's a more common differentiation. This is the one you use in band theory. The effective mass is just h bar dk, is change in momentum over change in the group velocity, that is the classical velocity. But we use our new d omega dk here, and then we've got a dk here, so I bring that down as a derivative. Okay, that makes a second derivative of the frequency, the dispersion function, to be more precise. And that means in band theory, you're going to be looking for this, if you were talking about effective mass, in a definition of effective mass that you should be using. So I've seen it used completely differently in many of the talks that have come by here. But in any case, you get the same thing. You get an inverse 3/2 power of 1 minus the relativity parameter. That's the old-fashioned formula. And this is a simple formula. And it's the exact thing. There's no approximations here. So basically what you're looking at a dispersion curve, and you're saying how easy, how malleable to change in velocity are the waves that are on this curve. And you can see very quickly that we're talking about a second derivative of this thing. We start out, that's the minimum right there. That's the rest mass. But as you go out here, the circle of curvature, okay, for this thing gets bigger and bigger. The radius gets bigger and bigger. It gets straighter and straighter. It's approaching an asymptote, this hyperbola here. It's approaching a straight line. And the smaller the rest mass, the quicker it gets there. But anyway, what you're getting to the point, you see, where the effective mass goes to infinity. So that is, I think, important to notice about, that's what waves do. This hyperbolic dispersion gets very short. Now, light itself has an infinite effective mass. That is, it's on the asymptote here, or on any part of the light cone that you want to look at. And that means that it is not able to accelerate. It's going C and it isn't going to go anywhere else. That's our basic axiom, is that C is not going to change for a single CW. It's when you get two of them together that you get to play all the games that mass does, and then some. So this is getting us pretty much here. Now, Newton complained about his corpuscles of light. That's his whole book on optics is about light being corpuscles, that is particles. And he said that they have fits, and that's what they have when they interfere and make weird patterns that he could see. I mean, if you look carefully just at light onto a shiny piece of bronze or something, you can begin to see that. A sort of a speckly thing going on. He says it's crazy, it's absolutely crazy. But all of this, here's the photons thing, a gamma rest mass. Okay, no, it does no gap. There is no gap, MC squared gap, for this thing if it's a single CW. Okay, so that is absolutely zero. Okay, the momentum mass, you can write that very nicely. P over C, that's h bar k over c, or else h nu, frequency of the light, divided by c squared. Okay, and you can see here that we have once again, the denominator, large number, okay, and then a small number sitting here fighting that, or I should not fighting, going along with it, and then nu could possibly be a large number, okay. So this one is an actual formula we can use, okay. But what's the effective mass? Okay, effective mass is just infinite. That's light, single light by itself, not able to make a dispersion function. It's just a straight line in omega k space. And in space-time as well. Okay, typical momentum, 10 to the minus 36, momentum mass, 10 to the minus 36 kilograms, for 600 terahertz. And I haven't said how much of it you're getting, this thing you multiply by quanta. Okay, now, the relations that we may have time to look at just really briefly, and this is where the Lagrangian comes in. Lagrangian as a derivative of this thing we call phase. And there's the phase, the way we've written it, for just doing wave mechanics here. Now, we're going to be writing it out using all this new stuff, or this new connections, okay, so that we can get both momentum and energy in, nice formulas that we can make sense of. And that is a number of things that we've talked about in this class, like the Legendre Transformation. Okay, here it is. Px dot, that's this guy right here, okay, minus the energy, that's the Hamiltonian, that's our Lagrangian. It's a derivative of phase. Locally, with the mass And now, as you see it go by, you may see a different derivative of it, and that'll be the Hamiltonian, roughly speaking. So one of them's local, the other one's global, so to speak. And also one of them is on the diagram just as a circle, and the other one is a hyperbola. So we go ahead and work all that out, compare the Lagrangian, that's what comes out of this, very, very nicely. The Lagrangian is the thing that was called the Lorentz contraction factor. This time it's got an MC squared. So the hyperbolic secant that lives on this circle. There's the Lagrangian circle right there. Okay, and you see the Lagrangian circle has the same curvature, but with a minus sign because it's pointing downward, as the hyperbola in this neighborhood. Okay, so they're both p squared over 2m, that's what the Hamiltonian would be, or 1/2 mv squared, group velocity squared, that's what you'd be writing for this with a minus sign. So that's a key thing to note about these functions. Okay, that hyperbolic secant is definitely part of the story on these, in this geometry. Okay, so let's see if there's anything else I can mention here. This is just working out the Hamiltonian again from the hyperbolic cosine, and this one from the hyperbolic secant. Okay, and this one, this is kind of interesting. This is the Lagrangian giving MC squared times the cosine of sigma. Okay, the cosine of sigma is the same as the sec of rho. Okay, remember the way these things are situated in this table, the secant right here, and the cosine right here. Secant of the rapidity, the cosine of the stellar aberration angle. The waveguide k-vectors, a polar angle is what it really is. So all of that is kind of shown on this graph right here, and I'm going to jump ahead on this one to that point where we can just, for sake of argument here, go ahead, and this is always a computer that gives me a headache when it comes to jumping to a site on the web, but let's just give it one more chance where we make nasty names about it. There it does its thing again. I've got to figure out a way to get around that.
I need to quit Firefox completely.
Yeah, that's kind of what it's asking me to do, and I have done it. So let's go back here and see if it'll go this time. No. Well, we're going to have to fix that bug. That's really nasty. But let's go over here and see if this guy will bring us up. And there we are. Okay, so this is this graph. I'm going to swell it up here. You do that just by working a little mouse wheel. What this is letting you do, of course, and if you click and drag, you can put all of the other side of quantum mechanics, which is the stuff that's going back in time, the antimatter, out of sight, out of mind. But this sort of geometry is just copied down below. And that, and I'm going to try to get this one back from the dead, because I want to show where all of this is. Okay, the basic idea that's not shown here, and you can see it at the bottom of this screen, is that Lagrangian, it is the sec, hyperbolic sec, is minus mc squared, so it really starts at the bottom here and then goes up with a parabola mv squared over 2. Mu is our group velocity. So here is the group velocity. Here it is right here. That's the the hyperbolic tangent times the b. Now we really need to scale to give the right units. And then this one is that same b times the hyperbolic secant. So that's the Lagrangian right there. There's the Hamiltonian right there. That's the hyperbolic cosine that goes up and meets right here. This is all hyperbolic cosine from there to there. That meets the momentum, which is the hyperbolic sine. So we're just repeating the things that we have right here. That's the momentum. And there's the Hamiltonian being a function of momentum without the blessings of the Pope and the canonical friends. Right? This is why you really have to make something that is going to get infinitely large on this hyperbola with an infinitely large momentum as to being different from describing it as you would in high energy physics by something that never can get past the speed of light. The group velocity is ending right there at c. Okay? And it's this function that you see at the bottom of this still here. We don't have it quite in place, I don't think, on there. But anyway, as I mentioned already, might as well do it again now that you see a little bit more what this is. As I work myself off into the distance, you can see the Rayleigh wavelength getting really short. And damn it, I always forget to turn off the swindlers. Okay. In any case, what you're noticing is we're coming down the Lagrangian here, approaching the speed of light, and the Lagrangian is this distance right here. So it gets, for high energy, it gets kind of small. It gets to be a small number, whereas the Hamiltonian is taken off. But you see, high energy physicists are all within a pixel of this point, and us, the molecular, atomic, and optical physicists, we're within a pixel of that point, right? So we use Hamiltonians very happily. A Hamiltonian is a reasonable thing, and most of the time we subtract off MC squared, so that's our Hamiltonian, right? And we just put this thing right at 0. The trouble is when you do that, the group velocity becomes faster instead of slower than the phase velocity, so don't do it if you're playing wave mechanics. You need that MC squared. And even when living in this neighborhood here. Okay. Well, anyway, the Minkowski graph, of course, covers the whole per space-time. We've only shown one little piece of it right here, and you can easily adjust that by playing with the controls to see how it affects things that are outside of there. I don't think there's much else I need to describe except that the stellar aberration angle, that's this thing right here that we've drawn in orange on the board over there. You can see it's the lower edge of the Occam sword. Okay, and it's the k vector. The k vector ends right there. As you go faster and faster, the components of the k vector perpendicular to your motion do not change. But boy, this one sure does, and it starts to become very high frequency. As I said, as the stars move in front of you, look out, that light's bad. Light's got a lot of energy. Okay, I think probably the best thing here is to stop. There's a whole nother lecture about how transitions occur, how Feynman diagrams work. You're absolutely welcome to, look at that and come and ask me questions about it. I'll be happy to talk about this stuff, as you probably already have seen. In any case, thanks for your attention this whole semester, and I hope that some of this will catch you. Okay? Any questions? We have, certainly you might want to just stay around and ask them privately, but if you want to do it globally, you're welcome to at this point. You can see, probably have the same feelings probably that Stephen Chu had.